Welcome to the deep dive, everyone. Today we have a really specific piece of hardware to look at. We are digging into a spec sheet for the DVIGear DVI-2310-SHRD. It's a dual-link DVI-D 10-meter cable, and it costs a staggering $225.
Right. Yeah, for a single 10-meter cord, which, I mean, that sounds completely wild at first glance.
It really does. I mean, okay, let's unpack this. Why on earth does a mere monitor cable require this level of, extreme engineering?
Well, the spec sheet explicitly says it's built for mission-critical applications. So, environments where you absolutely cannot afford a single dropped pixel.
Right, like a high-stakes server room or a medical display. Because we all know standard copper kind of degrades over long runs. It's basically like a leaky garden hose, You lose a few drops of water. It's usually no big deal for a home setup.
Exactly, but you can't have a leaky hose in an operating room.
Exactly. This DVI-Gear cable has to act like, I don't know, a high-pressure industrial pipeline where absolutely zero data escapes.
Yeah, and building that pipeline requires a completely different approach to the physical construction of the cord. Because over long distances, high-speed digital signals naturally degrade. You get signal loss, skew, and jitter.
Which brings us to the actual anatomy of this thing. The specs list heavy-duty 22 AWG, copper, and triple shielding. Now, we know shielding keeps outside electrical noise away, but what is going on mechanically inside to justify that massive price tag?
So it really comes down to lowering resistance. That 22 AWG copper is exceptionally thick for a display cable. And thicker wire means less electrical resistance.
Oh, right, which preserves the signal over that full 10-meter run.
Exactly. And when you combine that with the triple shielding plus the connectors themselves...
Wait, what about the connector?
They have 25 individual pins, and each one is coated in 30 micro-inch gold plating.
Wow, 30 micro-inch. That is a serious physical defense mechanism against, long-term physical corrosion and signal decay. And it says here it's also green-friendly, right? RoHS compliant.
Yep. It meets strict environmental safety standards. But the physical shielding is really just the start of the story.
Yeah, because here's where it gets really interesting. Looking at these specs, they highlight a feature called ultra-low skew. This deals with the internal timing of the data. Is skew basically like a synchronized swimming routine?
That is a great way to put it, actually.
Because if you're sending massive amounts of data across multiple twisted pairs simultaneously, and just one electrical signal arrives a fraction of a millisecond out of step with the others, the whole digital picture just falls apart, right?
That's the exact mechanical reality of it, yeah.
Yeah.
In a dual-link DVI setup, you are pushing parallel streams of data.
Right.
And if the manufacturing tolerances of those internal copper pairs aren't completely microscopic, some signals will literally physically travel faster than others.
Wow.
So ultra-low skew means the cable is engineered, so all the synchronized signals hit the connector at the exact same microsecond.
Which is absolutely critical when you look at the sheer volume of data going through this pipeline. I mean, this hardware handles dual-link PC resolutions up to 3840 by 2400 at 60 hertz.
Yeah, that's an aggregate bit rate hitting 4.95 gigabits per second. It's a massive amount of data to keep perfectly synced.
And it's doing all of this while being in-wall rated to survive anywhere from negative 13 degrees to a blistering 140 degrees Fahrenheit.
Right, because you're paying for the ability to install it in an incredibly harsh environment and then just, completely forget it exists. The infrastructure literally has to outlast the building's own temperature fluctuations.
But wait, I'm looking at the limits here and I'm a little confused. The manufacturer claims they support data transmission up to 60 meters, but the fine print explicitly warns that anything over 20 meters requires an active cable extender.
Yeah, there is a catch.
Right. If this highly engineered 22 AWG copper is so flawless, why does it hit a physical wall at roughly 65 feet or 20 meters?
Well, what's fascinating here is that you simply can't cheat physics. Specifically, there's this concept called insertion loss.
Insertion loss.
Yeah, even with that thick, high-quality copper, the electrical energy of the signal is eventually absorbed by the cable itself and dissipates as heat.
Oh, so the wire itself is basically eating the signal over distance.
Exactly. The 22 AWG wire delays that decay significantly, but by the time you hit that 20-meter mark, the insertion loss becomes too great for a purely passive connection.
Got it. So to reach that full 60 meters, you need an active electronic boost to physically force the signal the rest of the way down the line.
Precisely. You need active power to push it through at that point.
So stepping back from the spec sheet for a second, what does this all mean for you, the listener?
I think it reminds us that true digital reliability isn't just, software magic. It relies on exact, highly engineered physical hardware.
Right.
It's built to microscopic tolerances just to ensure a really fragile digital signal survives extreme real-world conditions, like that 140-degree heat, without dropping a single pixel.
It really does make you look at your own office walls a bit differently. I mean, if a simple 10-meter connection requires triple-fielded copper, ultra-low skew, and precise gold plating just to guarantee an image appears on a screen without jitter.
It's a lot of hidden work, yeah.
It is. It leaves you wondering how much highly engineered, completely invisible physical infrastructure is silently operating inside the walls around you right now just to keep your daily life running.